Welcome to the next topic on the advanced earthquake engineering, which is the Pier analysis. In your syllabus, it is a unit number 4. So, unit number 4 is going to talk about the Pier analysis. At the same time, it will going to address the important criteria about the masonry design. So, as per the masonry design is concerned, so we are supposed to refer the important codes available in literature. So, for that Indian standard 4326, Indian standard 1893 along with 13935, then 13927 and 13928. So, the problem we are going to discuss about this simple building. So, here we are going to discuss the problem about the masonry building, but same is also applicable for the shear wall, concrete shear wall, only there will be change in modulus of elasticity and the thickness of wall is going to change. So, here the problem statement is we have considered one masonry building, it consists of one door, one window. The top of building is having the rigid diaphragm, means there will be the top slab on the diaphragm. So, it is not a flexible, it is a rigid. So, we will have the different piers in this wall. We will try to bifurcate this wall into the different piers. So, the force of 100 kilonewton is applied at this point. So, the other dimension, so this is 0.5 meter, this is 1.5, the 1.5 by 2 meter will be the dimension of door. The window dimension is 2 by 1.2. So, these other dimension, the total length of building is a 6 meter, the height of building is 3.5 meter. So, let us start with the analysis. So, in the pier analysis, the important task is to the nomenclature or to name the piers, which is called as the nomenclature of pier. So, let us start here. So, I will bifurcate the given structure into given wall into different pier. So, this is the first identifications where there will be sill beam, sill level, it is called as the sill level. Then the other bifurcation will be the lintel level at this door level. So, I will name these piers accordingly. I will start from this pier. So, I will call this is 1, this is a 2, this is the pier 1, this is the pier 2, this is the pier 3, this is the pier 4 and the last one, this will be the pier 5. So, in our discussions there will be 5 different piers. Now, the methodology available in ASC 41, let us try to discuss, or I will discuss what the formulas we are supposed to implement in this analysis. The important task is to work out the stiffness of the wall, So, the stiffness is generally referred as K or R. So, the formula available in literature in ASC 41 will depends upon what will be the boundary condition of each pier. So, if you try to focus on pier 5, so the boundary condition is the top end is free and the bottom end having fixity. For other piers 1, 2, 3, 4, the top end is fixed and bottom end is also fixed. So, what is the formula? So, the formula we should use will be the R is the stiffness of pier. So, it is governed by E times T. E is the modulus of elasticity of the material, T is the thickness of that wall and it is governed by the aspect ratio. So, H by L cube 3 times H by L. So, this formula is applicable when it has having fixed end at or it has having the fixity at two ends, fixed at two ends. There will be little deviation in the formula. So, the R will be different for the pier like a 5, which has the top end as a free and the bottom end is again fixed. So, E t divided by 4 times h by L cube 3 times h by L. So, this is for free one end, while other is fixed. So, we are going to use these two formulas in the analytical procedure. So, this is the pier 1, pier 2, pier 3, pier 4, pier 5. So, by using this formula, these two formulas, we will try to quantify what are the different stiffnesses in terms of E t. So, we will keep the E t as a constant. So, in this problem, for understanding, I will make the problem little live. Little live means we will consider the value of this E. So, I will assume this is a masonry building. Later on, we will see the different material and different thickness. So, the E will be 3500 megapascal if it is a masonry structure. At the same time, I will consider the thickness of wall as 230 millimeter. And one more task we will try to induce in the problem. We will try to find out what will be the deflection for the top. So, this will be the deflection we are going to quantify here. So, this delta we will try to identify. So, let us come to the this evaluation of the stiffness. So, the first step number 1 I will call evaluation of stiffness of pier of piers. So, h will be the height of pier, L will be the length of pier. So, h by L is the governing parameter, which is the aspect ratio of this pier. So, for pier 1 I will write, for pier 1 the h by L will be, this is pier 1, the height is 0.8. So, this will be 0.8 divided by 2 plus 1 plus 1, 4. So, it comes to be 0.2. So, I can compute the value of R 1. So, in terms of E t only. So, E t divided by this 0.2 cube plus 3 times 0.2. So, this will be the stiffness of the pier 1 in terms of E t value. So, this is 1.65 times E t. So, we will substitute the E and T later on at the final stage. Now, similar formula we can implement for computation of piers 2, 3, 4. So, for pier 2 now, the h by L will be, the h will be now 2 meter, L is 0.5. So, h by L will be 4, and similarly the value of R 2 now I will write here itself. So, R 2 is E t divided by 4 raised to 3, 4 to the power 3, 3 times 4. So, this will be the 0.013 times E t, this will be 0.013 times E t. Then we will consider for pier 3 as the 3 and 4 having the identical aspect ratio, identical size. So, for 3 and 4 the value of the R or value of the stiffness will be same. So, I will write here. So, R either 3 or 4 will be same. So, it will be E t divided by before that work out this h by L here. So, h will be 1.2 meter and L will be 1. So, it is 1.2. So, E t 1.2 cube plus 3 times 1.2. So, this is 0.188 E t. Next, for pier 5, the value of h by L, the h will be now 1.5 meter and the L will be entire length of wall. So, that is 6. So, this will become, this comes to be 0.25. Therefore, the value of R 5. Now, as this is the case where one end is free, therefore, we can implement the second formula from ASC 41. So, this is R 5. So, this will be E t divided by 4 times this 0.25 cube plus 3 times 0.25. If we work out this 1.23 E t. So, the step number 1 is over. So, in step number 1 we have tried to quantify the stiffnesses of different piers. So, in our case we are having the 5 piers. So, these 5 piers we have quantified in step number 1. So, in step number 2 now, the step number 2, we will try to implement the spring analogy here. So, the spring analogy, what we have learned in structural dynamics, the same we will try to implement to understand how the distribution of the force will be there in the different piers. So, I will draw the sketch. So, we will start from the bottom side. So, bottom side, this is resting on ground. So, I will consider this 6. So, the stiffness of first pier I will consider here. So, I will mark this stiffness as R 1. Then similarly, this is having connection with the pier 2, which is immediate to the R 1 or pier 1. Therefore, this will be the R 2. Now, if we look at the 3 4, the location of pier 3 and pier 4. So, both these piers are arranged in series with one, at the same times both these piers are parallel to each other. So, that logic we will implement here. So, this will be now R 3, R 4, and again both these have come together and they are having the common pier at top. which has the stiffness of R 5. So, this is how the piers are arranged by considering the spring in series or the spring in parallel. So, depends upon location of the pier with respect to each other. Now, we will try to find out this R 5, and the force on this R 5 is obviously 100 kilonewton. This is about the step number 3, step number 2. The step number 3 is estimation of forces in pier. Piers. So, obviously, we will start with this end. So, I will write here the force in pier 5, that will be obviously 100 kilonewton. Then I will write here the equivalent stiffness of these two spring. So, I will write the R 34. R 34 is nothing but the addition of R 3 plus R 4. We have considered these two spring in a parallel, or it is nothing but the addition of K 1 plus K 2 like that. Okay. So, it is similar to the K 3 plus K 4, which we will consider as R 3 plus R 4. So, this addition will comes to be how much? So, R, we have estimated this individual value. So, it will be 2 times of single value 0.188 or times 80, it will comes now 0.37680. Now, we will try to find out the stiffness of these two springs along with one. So, we will try to arrange now the combined effect of these 3 4, which will represent as stiffness 3 4, which is in series with R 1 as R 134. So, for this we will use the formula. So, 1 divided by 1 upon R 1. So, R 1, what is the value of R 1? 1.65 ET, 1.65 ET plus 1 divided by this 3 4 is 0.376. So, if we work out this, we will have the equivalent stiffness as 0.306 ET. So, this is the important step. So, depends upon the analogy of the spring, we are supposed to find out the stiffness of this. So, I will remove this. Now, this comes to be 0.306 ET. So, our interest is to find the force in pier. So, 0.306 134. So, that diagram is required. Therefore, I will use this place to and redraw the diagram one more time. So, this is R 1, R 3, R 4 R2, R5, 100 kilonewton. So, we have now estimated the value of R134 as 0.306 ET. We have distributed the force in 5. So, there was no bifurcation while considering the force in pier 5. So, it will be 100 exactly what the force is applied on the pier, but there will be now distribution, and this distribution of the force will depends upon the stiffness of that pier. So, we have estimated for this R134. So, now if I want to estimate the force in pier 2, so the force in pier 2 will be R2 divided by R2 plus R134. What is the equivalent stiffness of this R134, and this will be multiplied by the 100 kilonewton, which is the applied force. So, if you substitute this, then it will comes to be 0.013. So, ET is going to compensate with each other, it will going to cancel. So, 0.0113, 0.013 plus 0.306 multiplied by 100. So, this comes to be 4.07 kilonewton. So, force in pier 2. So, let us see here, the 100 kilonewton force is applied at the top of wall, but so 4.07 kilonewton is the force in pier 2. The remaining part of the 100 kilonewton will be the obvious force in the combination of piers 1, 3 and 4. So, I will write here. So, this is very important step. So, force in pier 1, 3, 4 will be 100 minus 4.07. So, this will comes to be 95.93 kilonewton, which is the force in this 134. I will remove this now. Now, what will be the force in pier 1? So, force in pier 1 will be the same force. What the effective force we are going to get by subtracting the contribution of R2. So, that will be the net force carried by the R1. So, R1 or F1 you can say will be the same as the force in pier 134. So, that will be the 95.93 kilonewton, and the force in pier 3 or 4 both are same. Therefore, whether I can consider the 3 or 4, the meaning is same, will be the half of this. So, 95.93 divided by 2, 47.96 kilonewton. So, this is about the distribution of the forces in a different pier. Now, the next step number 4 you can say is the equivalent stiffness of system. Stiffness of, I will write wall. So, this will be the R, I will consider now entire thing together. So, R 1, 2, 3, 4, 5. So, this will be 1 divided by 1 divided by, we know about R 1, 3, 4. So, which is going to add to the R2 as this is arranged in parallel with this. So, I will write here. So, I know the value of R 134. So, what is the value? 0.306 plus about R2 I know 0.013 ET plus 1 divided by 1 plus 1.65 times ET 1.23 ET. So, if you work out this, then 0.253 ET. So, this is the equivalent stiffness of entire system. I will write now the values of the different forces involved. So, this is having 4.07 kilonewton. Then in wall number 1 it is having 95.93 kilonewton. In wall number 3 we have 47.96 kilonewton, 47.96 kilonewton is again the same value, and here it will be the 100 kilonewton. Why I am writing these values in the equivalent Pier designation or Pier nomenclature? The meaning is I can able to compute the structural entities like a shear force and bending moment anytime. So, we got the value of equivalent stiffness of wall. From this equivalent stiffness of wall, we can able to find out the displacement or the deflection of the wall. So, the deflection of the wall I am going to delta, then delta will be F divided by R. So, F value is the applied force 100 10 to the power 3 in terms of Newton, R is 0.253 times ET. Now, we will substitute the relevant values of E and T. So, E is now 3500 and thickness is 230. So, if we work out this, then it will become 0.491 millimeter, and if it is a case of masonry structure, then obviously this value is less than 1 mm. Therefore, the structure is not having any kind of crack. So, in case of masonry wall, if you refer the literature, so 1 mm is the maximum permissible deflection or displacement. So, after 1 mm the masonry is going to crack. Now, the question is, if I am going to change the instead of now assuming it is made up of masonry, if I am going to consider the other material like concrete, then the logic will be the same, the procedure will be the same, only there will be change in these two values, and how it is going to reflect this deflection criteria we will try to understand. So, I will consider now deflection if wall is assumed as concrete wall of M30 grade, M30 and thickness of 100 mm. So, only the variable will be the ET value. So, it is 100 10 to the power 3 0.253 into here it will now going to change. So, it will become 5000 under root 30. So, 5000 under root FCK will be the value of E in case of concrete multiplied by 100. So, if you work out this, then we are going to get the value as 0.144 millimeter. The idea is, as the E and T we can change any time. So, accordingly the replacement will be there for this substitution, which is related to the thickness of wall as well as the modulus of elasticity of material. The last one more thing that we can able to get from this analysis, we can able to get the value of or the quantum of the shear force and the bending moment in all piers. So, at the end we will try to consider the all piers together with equivalent amount the shear force and bending moment. So, I will write here the pier, then I will write here the force, then I will write here the shear force, and finally we will end up with the bending moment. So, I will start with the pier number 1. The force in wall is 95.93. What will be the shear force? The shear force will be the obviously same 95.93, but there will be change in bending moment. So, this is having fixity at the base, therefore, the bending moment will be the 95.93 into h by 2. H is how much? 0.8 multiplied divided by 2. So, this will be the value of the bending moment. So, the pier, then I will write the force here in kilonewton, the shear force in kilonewton, the bending moment we will consider in kilonewton meter. So, this value is how much? 38.33 kilonewton meter, or we have considered this. For pier number 2, the force is very less, 4.07, the same will be the shear force, and the bending moment will be 4.07 multiplied by 2 by 2. So, it will be same 4.07 kilonewton meter. For 3 and 4, the value of force is 47.96 kilonewton, the same will be the shear force, and the equivalent bending moment will be 48.96. The height is 1.2 divided by 2, 28.77, and for last pier 100 kilonewton is the force, the shear force is 100 kilonewton, the bending moment will be 100 multiplied by the height is 1.5 divided by 2. So, this will be the 75 kilonewton meter. So, hope you understood the procedure to complete the problem. Thank you.